Looking at several sections today, we're going to lump together sections 110 through 113. And as you can see by the screen, there's some different things that we're looking at. Continuity is going to be a big topic on this one and throughout the rest of our course. We're going to describe those discontinuities as removable, non-removable, and then talk about some of the discontinuities that you talked about in pre-calc, jump and hole discontinuities, unbounded. So here we go. So continuity implies that there's no interruptions in the graph, that I can smoothly trace the curve without having to pick up my pencil and hop up to another part of the graph. So how would you define that? It's easy to describe, but let's put it in mathematical terms to define it really carefully. And let's see here. Definition of continuity. Continuity at a point. It says a function is continuous at some point x equals c where these three conditions are met. 1, f of c is defined. That means that we have a point. You know, you'd have some ordered pair, c, comma, some value for y. Then I have number 2, it says the limit exists. The limit exists of f of x as we approach c, so the left and the right agree. And the third thing, which ties both parts 1 and part 2 together, is this notion that the limit must equal the point. And so if I think about this, if I have c here, and I want to plot out my point, let's say we've got a point right there. So 1 exists, I have a point. 2, the limit exists, then the limit exists, it could look like this. I have a limit, the left equals the right, but you'll notice my graph is not continuous right now as the way I drew it. And that is because I need this step number 3 to complete this process. Oops. I want this curve to be right in line with that point so that the limit value equals the y value from that point. Okay? So that is what continuity is. And it says a function is continuous on the open interval a to b when the function is continuous at each point in the interval. A function that's continuous on the entire number line from negative infinity to infinity is called continuous everywhere. So there's no holes or gaps on the entire x-axis of values. So over in the right you have a box, yep, and it just says, in order for a function f of x to be continuous at point x equals c, the following 3 conditions must be met. See if you can spell them out. F of c exists, or is defined. That means the point exists. The limit exists as we approach c of our function f of x. How do you prove they exist? Typically, you just state the value that they are. And then number 3, to tie it all together, the limit must equal the point. So get that stuck in your head. If you're asked to prove continuity on a test, you must step through those 3 pieces of continuity. That is how it's defined, so that's what the AP expects you to be able to write out. All right, 3 examples of discontinuity on this open interval a to b. F of c is, well, there's c and I have a hole. Looks like f of c is undefined to me. And we call that point discontinuity. You also sometimes might hear it referred to as a hole or hole discontinuity. They mean the same thing. Number 2a, the limit as x approaches c for f of x. Well, as I approach c, I'm just going to highlight the vertical line at x equals c. I notice that my 2 branches of the function of the graph are not connected. So we've got a discontinuity. This is called a jump discontinuity, and I'm trying to find a pen here. This is because the limit does not exist. So far we've seen reasons for discontinuity. One, the point didn't exist, and now here we had the limit didn't exist. 2b is unbounded behavior, and if I looked at the limit as I approach C, this also would have a DNE for an answer on the limit. Number 3, we have the limit. The limit is up here at some value, let's call it K, and my point has a height of M, so this would be the limit equals, not L, the limit turns out to be K, the f of C value turned out to be M, well, K and M were not equal. So this would be number 3, that it failed to show that the limit and the point did not exist. We call this also point discontinuity because of that open hole, and it wasn't filled in by that. All right, on the lower part there, it says an AP problem from 2011. Let f of x be the function defined by 2 branches, and one is a sine function and one is e to the negative 4x. Show that f is continuous at x equals 0. All right, so is my function defined at 0? So does f of 0 exist? Well, I look over here to the right, and I see where x is allowed to be 0, so I'm looking at this top branch of the function, and I do believe we are fine here. We'd have 1 minus 2 sine of 0, and what is the value on that? Sine of 0 is 0, so I'd have 1 minus 0, this would turn out to be 1. Cool, I passed kind of part 1 of my 3-part definition for continuity. The next thing I want to prove is that the limit as I approach 0 exists. And I won't know if that's the case until I branch out and look from the left and the right side of 0. So you know what, I'm going to do that work. I'm going to look at the limit as x approaches 0 from the right, and I'm going to look at the limit as x approaches 0 from the left of f of x. And from the right-hand side, I need to be larger than 0, so this would be e to the 0, which gives me 1. And then from the left side of 0, I'm looking at this branch, so I'd have 1 minus 2 sine of 0, and the sine of 0 is 0, so this gives me a 1. Does the limit exist? Absolutely, because left and right sides were equal. So the limit exists. Sweet. We now have 2 parts. We've met criteria 1. We've met criteria 2. Now, put it all together. Does 3 happen? Is the limit equal to the points? Yes, it is, isn't it? Because we got 1 equals 1. So I can say that f of 0 equals 1, which is equal to the limit. I'm just going to make a 3-way equality statement here, because it gives a little more information. So that is showing it is continuous. So then I'm just going to finish by saying, therefore, f of x is continuous at x equals 0. Awesome. Learn how to do that. Take practice when you're working on your homework. Walk through the 3 parts of continuity. All right. You may recall from pre-calculus that discontinuities fall into 2 broad categories. They are removable and non-removable. So we're going to, from the word bank, fill in the discontinuities, the type, and the graphical description of it. So removable and non-removable. There are 2 types of non-removable, And I am going to say one of them is the jump discontinuity. I see that word, so I've used that. We've got non-removable, removable. And the other one is the unbounded behavior, which would indicate an asymptote. You might even just want to put in there unbounded behavior coming off of that asymptotic behavior. And then we have removable. And the type of discontinuity that is removable is called a hole or point discontinuity. Looks like we've got hole here. Hole or point, whichever word you want to use to describe. Okay. This example number 1 gives us the graph. Lots going on. I see an asymptote, a vertical asymptote. I see quite a few open circles, so that's probably some discontinuity. The graph of f of x is shown. Determine all values of x where it is not continuous and classify each as removable or non-removable. So the first one I hit is right here. I would describe this as a jump discontinuity, and that would be non-removable. So I have x equals -1. Moving to the right, I have that asymptote. That is unbounded behavior. That is also non-removable. It's occurring at 1, at x equals 1. The next thing I pick up is a point discontinuity. And that is removable because all I have to do is redefine that and I can fill in the point. So x equals 3 as a point discontinuity. And finally at 5 there, we also have point discontinuity. Easy. Example 2, consider the graph, or consider g of x. List the x values where g of x is not continuous and classify each type of discontinuity. Write the intervals over the function for which the function is continuous. All right, let's get a deeper insight on g of x. And to do that, let's do some factoring. Okay, so 40, 4 and 10, 5 and 8, 5 and 8. 5 and 8 have a difference of 3. So x plus 8, x minus 5. For 10, things that multiply by to 10 are 1 and 10, 2 and 5. I'm going to pick 2 and 5 because they have a difference of -3 when I write it in that format. Now, what I notice is that I have x minus 5 canceling with x minus 5. So that means there's a hole at x equals 5. So x equals 5 is point discontinuity, which means that it is removable. I also have a discontinuity at x equals -2. It does not cancel with anything on top. This is going to be a vertical asymptote. So we have a vertical asymptote at x equals -2, and that is non-removable. And the final thing it asks us to do, write the intervals over which it is continuous. So we do have a couple spots where we don't have continuity. So it is continuous on -infinity up to -2, where we have that vertical asymptote. And then I'm going to join that with -2 up to 5, and join that with 5 to infinity. So basically we've just hopped over the -2 and the x equals 5 spots. Number 3, consider the piecewise function defined below for h of x. Determine all x values where h of x is discontinuous, classify them as removable or non-removable. Okay, so the last one, we used factoring and algebra to do it. The one before that, we had a graph. Now this one, they're giving us a piecewise function. So what concerns me on piecewise functions are the spots where they, hand off. So it looks like I'm coming into a linear function. Then I have a, what is that, a parabola, and then I'm back to linear, and then I'm more linear, something like that. How do these functions connect? If they connect perfectly, oops, if that just went flying. If this connects perfectly up, there's a chance that it could all be continuous. How do I look to see if that happens? Well, I need to know all these different y values of where those handoffs are happening. So I'm really interested in -2 at x equals 1 at x equals 3 to see what's going on there. So we're going to do some investigations. All right, so let's look at the limit as x goes to -2 from the left, because this would be left of -2, 2x minus 1. That carries a value of -4 minus 1, so that I get -5. Let's see what's happening to the right side of -2, and that would be x squared. So I'd have -2, oops, you know what, I need to write the function first before I evaluate it. X squared minus 9. And that's going to give me -2 squared minus 9. Looks like that's -5. And I need to know what's happening at 1. So the limit as x approaches 1 from the left side, that would be the function x squared minus 9, because I'm right there. Throwing in 1, I'd have 1 minus 9, or -8. The limit as x approaches 1 from the right. Now I'm working at 3x plus 2 for a function. That gives me 5. Ooh, that is not going to be continuous there, right? That's going to be a problem. I'm going to kind of chunk these off. And then lastly, let's look at 3. So the limit as x approaches 3 from the left, and we also want to look at 3 from the right. 3 from the left would be 3x plus 2. That would be 3 times 3 plus 2, or 11. And then 4x minus 1 is when I'm to the right of 3. So I'd have 4 times 3 is 12, minus 1 is 11. That matches up very nicely, doesn't it? So determine all the values where x or h is discontinuous. It is discontinuous at -1. The limit as x approaches 1 of f of x does not exist. And that fails then the continuity test. So this is discontinuous at x equals 1. And we have to classify it as removable or non-removable. Well, I left off at -8 and then I pick up again at 5. That is a jump discontinuity, which is non-removable. Okay. For number 1, or for not really number 1, but the first part of this analysis, the limit as x approaches -2 of f of x was equal to -5, and the function's value, f of -2, is -5, so it is continuous at x equals -5. It says continuous, not very well written there. All right, what about our very last thing? It is like the first, where we have continuity because the limit exists and, oh, whoa, maybe it's not, because I do not have it defined at 3, do I? Okay, so let's summarize this. We have the limit as x approaches 3 of f of x equals 11. But what is the value of f of 3? I do not see any equal sign under either of those spots, so f of 3 is undefined. And so we have discontinuity. Where should I write this? It is discontinuous at x equals 3 because it is a whole or point discontinuity. And that is removable. Very good. And finally, example 4, the piecewise function for k of x is shown below. Find the values of a and b that make k continuous everywhere. Be sure to use the definition of continuity and proper notation when you work on this. Okay, so this is kind of like last time. Piecewise function, we're concerned at the 2 handoff and the 3. So let's do our analysis and see what's going on. The limit as x approaches 2 from the left would be x squared minus 4 over x minus 2. And that would look like the limit as x approaches 2. You've got difference of squares on top, so this will simplify down to an x plus 2. I'd have 2 plus 2 gives me 4. Let's also look at the limit as x approaches 2 from the right of k of x. That will be an ax squared plus bx plus 3, which if I plug in 2 for x, I will get 4a plus 2b plus 3. And for the limit to exist, because we are trying to make this continuous, we want to make it continuous, then the limit as x approaches 2 of k of x would need to equal 4. So I can make one nice equation right here, and that is that 4a plus 2b plus 3 equals 4. You know what, let's simplify that out. Subtract 3, and I'm going to have 4a plus 2b equals 1. Sweet. Now let's go look at 3. So we do the same type of work again. The limit, whoops, I thought I changed colors. The limit as x approaches 3 from the left will be this function, ax squared plus bx plus 3. Plug in 3, because we're approaching 3 from the left. I would have 9a plus 6, no I wouldn't, 3x plus 3. From the right side, the limit as x approaches 3 from the right of 2x minus a plus b, plug in 3 for x, we're going to have 6 minus a plus b. For the limit to exist at 3 for k of x, I need the left side and the right side to be equal. Let's just write exist. This one isn't quite as easy to write because we don't have the number like we do last time. So we've got this part and this part. I need 9a plus 3, 3b. 3b, because I put in 3 for x. 3b plus 3 equals 6 minus a plus b. And like that other one, let's get a's and b's on the same side. So I'm going to have this equals 3, added a over. I'm going to have 10a subtracted b. I'm going to have 2b. 10a plus 2b equals 3. That's not what I have on my notes, so I must have a mistake somewhere. I have 9a, minus 3b. Should that be minus 3b? Don't think so. I think I've got a mistake in my notes. We're approaching 3, aren't we? We put 3 in here, giving us 9a plus 3b. And then the other one put 3 in, we have 6 minus a plus b. Okay, I just have an error in my notes. Therefore, I want to take this and do a systems of equations to solve it, and then I'll have my a and b. All right, so let's go. 4a plus 2b equals 1. I'm going to take the opposite of my second equation, giving me negative 6a equals negative 2. It appears that a is negative 2/3 over negative 2 over negative 6, giving us positive 1/3. And then go find b by plugging in 1/3. That is enough for now. My lights went off in the room, so let's call it a day there. Here is the worksheet that you'll be working through, all the continuity and discontinuity, removable, non-removable information that we just learned. Have a great day.